now on the back side of the Funeral Mountains Metamorphic complex. So that sort of ridge over that way is sort of the core complex. And we're right now in something called the Titus Formation, Titus Canyon Formation, which is these set of round cobble fluvial conglomerates and fanglomerates. And they're basically what they are is a supra detachment base system basin. When you have one of these big core complexes, you know, you're uplifting the footwall and you've got a bunch of erosion. At the same time, you're dropping on the hanging wall. You make this big basin, and they tend to collect these terrestrial deposits. So these would have been, you know, deposited by streams and things on land. Interesting about Titus Canyon Formation is because this, so the age of the Titus Canyon Formation is lower Oligocene, so that would put it probably in like 30 million years old or something like that. But at any rate, the interesting thing is because it kept shearing along the attachment fault after these conglomerates were deposited, is if you look around, you can find cobbles that have been sheared into pieces, but they were done so under enough pressure that it's still sort of stuck together. So you can find cobbles that are like fractured into this isn't a great example, but sometimes you can find one where it's like it basically looks like it's a shattered pebble that's still held together. Anyway, we'll look for some. Yeah, so something like this. Sometimes you'll have one where it has even more offset on it, so like it looks like it's like sort of stretched a little bit or something. Yeah, like this guy here it has some good little faults across it that are healed up. Although I think the GoPro only focuses if it has a background at the same distance. There we go. Okay, so we are now descending into the core of the Funeral Mountains Metamorphic core complex. And so right here we're going to contact these some light-colored rocks and some greenish rocks. The light-colored rocks are basically upper crustal rocks that are totally, basically unmetamorphosed. And then these green rocks, well, we'll look at them, but these are basically now green schist facies, which explains why they look like green schists, basically. Now, the boundary canyon detachment, as we'll hear later, is not a single one fault. There are actually additional faults we'll cross later. There are a bunch of these sub-parallel low-angle faults that all would have had similar senses of motion. And so in general, you might have gotten disoriented here, but it would have been top moving that way motion. So when we looked at this at the Funeral Mountains from the other side, it was sloping down. So it's sloping down to the west that way, and it slopes up that way. So the hanging wall was slid off towards these outcrops here, over the top of them, basically, sort of perpendicular to the canyon. So anyway, we'll come look at these rocks a little bit, but that's the main story here. Okay, so now we are in the core of the Funeral Mountains Metamorphic core complex, where there are amphibolite facies and rocks from the middle crust exposed up here, as you can tell by the gooiness of the folds here, to use a technical term. And this will also be our camp tonight, just to give you guys a panorama here. So here we are descending down into the lower parts of Monarch Canyon. We're going to be looking for kyanite schists and true amphibolites and other indicators of rocks that have come from the mid to lower crust. Brought up by this metamorphic core complex. So this is our journey down into the earth. so here we have some nice schists. The minerals are a little too small to really identify, but they look like calc-silicate schists actually. It's probably diopside and calcite, but it's hard to tell. They're kind of fine-grained. Public service announcement. So we're going to walk through the brush down here. Just keep your ears out for rattlesnakes. Last time there was a rattlesnake hiding in the brush, so you know, watch out for them. It's probably cold enough they're hiding in their little burrows right now, but you never know. Some nice folding of these yellow and brown rocks here. So question for you guys, what age is the rock we're standing on right here? What is it? It's nice. So I've asked the question to the people who got here already of what's this rock we're standing on and how old is it?
It looks like a breccia.
Are the class angular? I guess they're a little angular. I would just call this a conglomerate. Okay, and the second thing is how old is it? I think you can be more specific with that. So what kind of depositional environment would you get this kind of deposit in? Maybe a landslide. I'm going to say it's actually too well sorted for a landslide. River, basically, yeah. I mean, basically a debris flow. Where would you get a debris flow like this in the modern environment? Right here. I mean, if we got a real big rainstorm right now, like a big debris flow could come down through and it would look just like this. This deposit here is probably less than 10,000 years old. You know, in areas where there's a lot of carbonate rocks, the carbonate acts as cement, and it'll lithify rocks just like that. Like in places with carbonates, I've seen rocks. I literally found a nickel that had a date on it from like 1974, stuck in a carbon cemented beach rock somewhere. So in places with carbonates, you can go from lakes, you know, gravel like you see down there. See, it's the exact same color. See this color of the gravel, the color of this, the exact same color of tan. This stuff probably is not that old. You know, the way we know it's really young is because it's, you know, the modern stream hasn't cut that far down into it. So there's basically this terrace here. Okay, the modern stream has cut down maybe, you know, 3-4 meters down since it was deposited, but that's not very far. So yeah, basically this is probably, okay, it could be older than 10,000 years, but it's probably younger than 100,000 years for sure. Okay, that is all. You can see some nice buttress unconformities here. See how the bottom of the canyon has the has this conglomerate in it, and it's sort of pasted onto the walls. Okay, so let's look closely at this rock here. Tell me what it is and what metamorphic minerals you find in it. So for you television viewers, just notice there's a little bit of a blue shine to this rock. I think the camera's gonna go out of focus before you can actually see anything, but that's okay. So we're just gonna continue our walk today. We're just gonna go up the canyon and check out some of these outcrops. So we'll just start right here next to camp. For those of you guys who didn't see when I pointed out last time, there's a great example of boudinage here. So boudinage is when you have a stronger feature, like in this case a pegmatite dike. You'll see this white rock here, come the blobs. Those are all pieces of pegmatite dike. And you have a more confident feature surrounded by more ductile metamorphic rocks. In this case, there's this sort of brown-gray schist above and below it. What happens is that if those rocks get stretched, the more competent rock will break apart into chunks, basically. And then the stuff will fall in between. So you look here, there's a bunch of chunks. 1, 2, 3, 4, 5 chunks here. And so each of these chunks, so this dike would have originally been about, you know, 1.2 meters thick everywhere. But then it got pulled apart. So then here it's necked down to this little narrow thing. And you can see here, there's this little fold here. This is a ductile fold where the ductile schist flowed into the gap between the two blocks of the dike that's pulled up. So this block and this block over here used to be right next to one another. Then they got pulled apart and it sort of sprung out this little neck in between. So this is the process. It's called boudinage. The individual blocks would be called boudins. It's from the French word meaning sausage. So it's sort of like a bunch of like sausages, like all in one sort of length. You guys have seen those before. So anyway, there's some great examples of boudinage in this canyon that we'll see. And again, it generally implies you have sort of stretching. If you look at them in detail, usually you can figure out the direction of stretching. So in this case, we guess it was left-right, but you really also need to look at the third dimension. I think you look at these closely, you'll find that the boudins actually sort of plunge that way into the mountain. So the stretching would be more like perpendicular this way to that, not necessarily perpendicular to the outcrop they're in. Yeah, so we're just going to walk up maybe quarter mile, something like that. There's just some good, neat sort of structural tectonic features. Look on this side, I think this is actually the same dike. You can see boudinage on this side in large blocks. This one also, you can see it's starting to pinch apart and neck into two different sausages there. Oh, there's that bag. But yeah, right where that bag was, you can see that neck of the two boudins coming apart. You see some nice ductile folding here in these calc-silicate rocks. Now, as we keep going up this way, we're getting closer to where the one of these detachment faults is, sort of at the top of these cliffy rocks. You'll notice that the rocks are getting so that, you know, down there's these big wavy folds. Here everything is starting to get a little bit more parallel. So here we're getting closer to the shear zone, and these rocks have seen more shearing. And we'll walk a little bit further up around the corner and look at these some more, but because I think they're but by the time we get up here to these blue rocks, these are basically marble mylonites. And so what do I say? What do I mean when I say a mylonite? Well, a mylonite is just a tectonized rock where the shearing has been extensive enough that it's reduced the grain size. So you look on the surface here, you'll see that it's actually really fine-grained marble, and it also has a distinct lineation to it. And so that's also characteristic of mylonites. So in this case, since it's got this lineation this way on it, you can tell the slipping must have been either that way or this way. Now, as for telling which of those it is, there are things we should start looking for. But before you start thinking about which direction did a shear zone move, you want to look for lineations, because, you know, this basically, you've got to narrow it down to at least two options. Because you start looking at random, you know, say we started looking at this face here and looking for indicators of shear, you know, if we're thinking of it shearing, you know, left or right in this sense, well, it doesn't make sense because the lineations say it must have been moving perpendicular to that. So if you look on a surface that cuts across the lineation, it's not going to tell you anything about the direction of shear. Yeah, so these are, so, you know, basically the fact that these marbles have this myelinitic fabric indicates that they were major participants in the shear zone that brought these mid-crustal rocks up towards the surface. So these are part of the detachment fault, basically. And as it turns out, you know, marble is particularly ductile, or calcite can deform ductilely down to particularly low temperatures. Calcite, you know, they're examples of marble benches that have actually begun sagging under people's weight in just a period of a couple hundred years. And so marble can deform ductily down to just a couple hundred degrees Celsius. And so, you know, if you imagine this coming out of the mid-crust, where it's starting at 400 degrees Celsius or something like that, at those temperatures, this stuff, you know, flows like toothpaste, basically. And so it's a good place to localize a shear zone. Specifically, this particular marble is probably the noonday dolomite, that same cliff-forming dolomite we saw at the War Eagle mine. If you were to compare the thickness here of this unit to the thickness we saw there was like an entire mountainside. Here it's compressed into a cliff that's maybe, I don't know, 30 meters high, something like that. So, you know, that along with myelinization, we get, when it shears out, it gets thinned out too. So it's not uncommon for myelinized rocks to be thinned by a factor of 5 or 10 or even up to 100 in some cases, although we don't see that here. And so, you know, if we're thinking about why do we get boudinage, well, again, if we're stretching it out that much, then you know, if say we had a quartzite or something layer inside of this marble, or just something coarser like this, it's going to be broken apart in little pieces. Yeah, this is a little piece of pegmatite dike here. So you can see there's just this little lens here, or there's another little lens there. So any pegmatite dikes that cross this, if this thing has been stretched by a factor of say 5 or 10, then the blocks of these dikes are then, this more resistant material is not going to deform ductily so much. So then they're going to be pulled apart in these little blocks. So if we know that there's lineations this way, we want to, if you want to think about shear direction, shear sense, so did it go top that way or top this way, you want to look for a perpendicular surface. So some of these surfaces here might be good ones to look at because they're relatively perpendicular. And the classic sort of things you want to look for are something called SC fabrics, which actually there aren't really very good ones here. Maybe over here. Well, we'll just spend some time looking at them. I might just stop. So up here, actually, we can see, we actually can see some more SC relationships. So if we look up here, there are these little dark bands here. So these bands here, if you look at them, these are actually more strongly myelinized bands where the grain size is even smaller. So these are basically what we'd call shear bands, which in the terminology of SC fabrics is what we'd call a C fabric. The C stands for cissement, which is French for shear bands, or something like that. And so then, if you then look at so those fabrics going this way, and then you look at other fabrics, they're dipping more this way, to the right here. That's sort of the main sort of foliation of the rock, is more or less what we call the S fabric, or French schistosité, or schistosity, which really comes from rocks that have a schisty appearance. But so generally, if you're looking at these two orientations, the motion basically is along the direction of the shear planes, because again, the shear planes is where the shearing is happening, and it's in the direction opposite the dip of the S planes. So if the S planes here are dipping down this way, the motion would be top to the left. Now again, you really should be thinking about, which way are those lineations pointing. And so this is not actually a great outcrop to look for shear sense, because our lineations are sort of going back into the cliff here at an oblique angle. But that's at least the principle of it. Maybe we look around the corner, we'll find some outcrops that are actually pointing the right direction. You see some more boudinage again in this cliff of another one of these big pegmatite dikes that's been pulled apart into blocks. Again, on the couple meters thick, but been pulled apart. So we start looking in this wall, which is perpendicular foliation. You can see these little clasts that have these tails on them. So here the tails are always being stretched out on the top to the right. Here's one, top to the right. Also sometimes these little knots of stuff, you can see it looks like they've been rotated. And so if it's top to the right motion, they should have sort of an appearance of clockwise rotation. So like this guy right here. So it should look like it's being pulled off to the right on the top and to the left on the bottom. So that would indicate a clockwise rotation into that. And so anytime you're looking at shear indicators, you want to look at a lot of these, because, one or two, you can catch something that, was confusing. But if you find like 20 of them and 18 of them are all pointing the same way, then that's probably the correct answer. I don't know about SC fabrics here though. It's mostly just smeared out. Anyway, so that's the other thing I'll point out over here is you can also see we're coming to the top of the cliffs here, and so the top of these represents that sort of lower detachment surface that sort of represents the top of the amphibolite facies stuff. And so, you imagine this stuff coming up out of the depths of the earth. It's sort of, there's not just one detachment surface, there's sort of different detachment surfaces. And so there's, we have a big break in up at that first detachment we saw, the Boundary Canyon detachment. We have a big break from sort of upper crustal stuff down to green schist facies stuff, which might be say 12, 13, 15 kilometers down. And then here we're probably, 20, 25 kilometers down sort of stuff. So it's fairly common these detachment systems to have multiple detachment faults that sort of stack on top of one another.